Hello, this is Unit 1.5, and this is Section 1, our Introduction to Sensation. Let's do this. So, what is the difference between sensation and perception? When you look at this image right here with the black and the white, how are you actually able to see that? Like, what processes are happening? You've got to have the image coming to your eyes, and then your brain has to process what you're seeing. Do you see two children looking face to face? Or did you see a vase? Or did you only see one or the other, but now you can see both? Why are you able to see one or the other or both? So that's what we're digging into here with sensation and perception. So, with a sensation, the outside world is constantly sending us stimuli in the form of light, sounds, chemical sensations, and all of that is raw data that's hitting our receptors in our eyes, our ears, in our nose, throughout our skin, on our tongue. All that is raw data. That is sensation when a stimulus activates a sensory receptor. But then we got to do something with that. We can measure it. A stimulus is measured by how intense it is, the duration of it, the wavelength, the size of it. Those signals will travel up our spinal cord via afferent neurons, and then our brain actually has to make sense out of it and interpret it. And that's where perception comes in. So, perception is the organization of the sensory information into something meaningful. Otherwise, it's all just lights and vibrations and chemicals, but we got to give meaning to it. The study of all of this is called psychophysics, how physical stimuli are translated into a psychological experience. So, the difference there again, sensation, we're representing the world. To represent the world, we have to detect a physical energy, some kind of stimulus in the environment, and then we have to convert it into something our brain can understand, into a neural signal. And that's actually called transduction. We'll get to that in a different video. All of that is sensation. And then once we have a sensation, we want to organize it and interpret it. And that is perception, which is happening constantly in our of Fechner. So a lot of what we look at in sensation are thresholds. So a stimulus, that's just any kind of detectable input from the environment. It could be a vibration, something that we can smell, something we can hear, something we can see. The threshold is the dividing point between what we can and what we can't actually detect. So another word use of the word threshold is a doorway. The threshold is whether you go in or out of a room or your house. So the threshold in sensation is whether you can detect that there's something there or that there's not. So there's a couple different theories on how we detect thresholds. The first is the absolute threshold. The absolute threshold says that there's a minimum stimulation for everybody that's needed to detect a particular stimulus about half the time. But half the time, this minimum, you will be able to get it. The other half, you may or may not actually get it. And when you see these examples, you'll see why. Now, I don't actually know who came up with these, but these are some classic examples of absolute thresholds. The weakest amount of stimulus person can detect about 50% of the time. For sight, it's seeing a candle flame 30 miles away on a clear night. Now, I would say you don't need to write all these down, but just kind of have an idea of what they are like. Hearing a watch ticking 20 feet away. That's really far. Can you hear the clock in our classroom most days? Touch, this one's great. Feeling a bee's wing falling a distance of 1 centimeter onto your cheek. So feeling a bee's wing landing there. Actually, I feel like I would feel that. Smelling one drop of perfume in a 3-room house. I feel like we need to operationally define what kind of perfume and how big this 3-room house is. And then taste. This one will be a tough one for me. Tasting 1 teaspoon of sugar dissolved in 2 gallons of water. So again, these are a minimum amount. What is the very smallest of a stimulus that you could detect half the time? The difference threshold, also through Fechner, who studied this, said that there's a minimum difference between 2 stimuli required for detection half the time. And he also called this the JND. So if the lights were already on, like in our classroom or in your bedroom, how much would the lights have to change, get brighter, before you noticed that there was a difference? So that's kind of what's being depicted here. Now, it's easy to tell when the light is turned off and then you turn on, the minimum. But When it's already on, how much does something have to change before you'll notice that there is a difference there? That's the JND, the just noticeable difference. Weber's law, and I think it actually has another German pronunciation, Weber, but I'm too used to saying Weber's, says that the just noticeable difference is proportional to the intensity of the stimulus, the initial stimulus. So if the initial stimulus is high, the just noticeable difference will also be large, meaning if the initial stimulus is like really loud, then we would need an even louder sound to notice that there's a difference. If the stimulus intensity is low, the just noticeable difference will be smaller, or it'll take less of a change to notice the difference. So if it's quiet, it wouldn't take that much of a sound for us to notice the difference. This is also called the Weber-Fechner law. Though I will say I've always just called it the Weber's law. So a couple examples of this, because this works with any type of sensation. So here with touch sensations and weight. If you have a full backpack, which is what most of you are carrying around a lot of the time, you're not going to notice when you add one more thing to it, like a spiral, or if you put your cell phone in your backpack, because it's just one more small stimulus added to a really heavy stimulus. If you added a giant biology textbook, then you would notice that. So since the initial stimulus is high, you're going to notice the difference only if the change that you add is also really big. If you start with an empty backpack and then you add something to it, like a bottle of water, then you're going to notice that. Starting with a lighter stimulus, you'll notice it right away if there's a change. There are experts in different sensory fields, people who can detect extremely small changes. Those people could work well as a food critic if they're able to taste differences. People who do smell testing for things like perfumes, those people would be experts at Weber's law. One more example that I always use has to do with sound. So let's say you go into the cafeteria in between classes during the day, and there's not a bunch of kids in there who don't have a teacher, like we have so many this year, but it's an empty cafeteria. When you walk in there, you're going to hear footsteps. You're going to hear your footsteps echoing in there. However, if you walk into a cafeteria at lunchtime filled with people, you're not going to hear one person walking in and hearing their footsteps. That's Weber's law. Weber's law says if the initial intensity is low, like an empty cafeteria, then you're going to hear a sound right away. It doesn't take very much. If it's a full cafeteria, so the initial intensity is high, you're going to have to hear, it's going to have to be a big change in sound for you to notice a difference, like lots of people walking in. The alternative to absolute threshold is signal detection theory. This one basically says that there's no absolute threshold, that our thresholds for what we can detect actually change based on our motivations and other competing stimuli. So signal detection theory predicts how and when we can detect a faint stimulus, that's a signal, amongst background noise. So it assumes there's not just any single absolute threshold, but it depends on other things like our experiences, if you're used to hearing something or seeing something, our expectations, motivations, and also how tired we are. Our level of fatigue can affect what we can detect. Signal detection theory says that we can have hits, misses, false alarms, and correct rejections. If there's a signal present and we thought there was one present, that's a hit. If we say we heard something, but there wasn't actually anything there, that's a false alarm. If we didn't notice anything and there actually wasn't anything there, that's a miss. But there actually was something there, that's a miss. If we say there wasn't and there wasn't, that's a correct rejection. Some other examples, real world examples, listening for the pizza guy, saying you know you ordered pizza to be delivered. So normally you don't hear like every car driving down the road, or you don't hear car doors opening and closing, but because you're waiting for that pizza guy, you can hear everything. And sometimes we're like, oh, did you hear a car door? And then there's no car door. So you had a false alarm. You thought there was something present, but there was nothing there. Sometimes you think like, I think I hear something, and then they're there, then you had a hit. Some other examples, searching for cancer cells, like if a radiologist is looking at x-rays, their experience level can help them to see or not see things, their motivation to really, really look, but also their level of fatigue. All of those things could affect their ability to see or to detect a signal. When we're home alone, we hear more things than we usually do when there's other people around. And then military patrols, again, expertise, experience, motivation, and fatigue can all play a role in what they're able to detect there. Another level of threshold is below our threshold, and that is subliminal perception. Subliminal meaning below. So when stimuli are below your conscious awareness, your absolute threshold for conscious awareness, then that's subliminal perception. For most people, these are things, signals that are not consciously detected. However, for some people, it is possible. The effects are very minimal. So, and I'll come back to perceptual set. So in the 1950s, there was a movie theater that had claimed that before the movie started, that they would flash messages on the screen. And then throughout the movie, they did this too. Things that said like hungry, eat popcorn, or buy a Coke. And they claimed that their sales for those products went up in the movies where they had those signals. Well, the public did not like this. They felt like, well, if they can, get us to buy stuff with these messages, what else can they get us to do? And people felt defenseless. So the government actually did studies about it, and they didn't find that subliminal messaging had much of an effect. Studies show that you can be primed, which means it would kind of, if somebody suggests it to you, then it might have an effect, but it's not going to have like any kind of significant effect on what you're doing. So perceptual set is the idea that kind of what you're already expecting and what your experiences and whatever your biases are will influence you. So it's kind of like if you were already wanting popcorn and then somebody asked you about it, then maybe this might have had an effect. But they're not gonna be able to put some kind of like dangerous messages on there and convince you to go do something with that. There's a couple different ways that we process stimuli as it comes in from the environment. Pre-attentive processing is automatic, extracting information automatically and simultaneously when presented with stimuli. But this can make it hard if there's competing stimuli, and we're going to do an example of this in class. So when there's lots of things going on, like someone's trying to talk to you, and somebody else is trying to talk at the same time, and you're like, wait, I can't focus. I just need to focus on one voice. That's attentive processing, where you consider only one part of the stimuli at a time. Selective attention is when you can consciously ignore some sensory output. So this girl who's trying to read in the park, and there's a dog barking, and it looks like there's maybe a party back there, a fire truck, and this guy on his cell phone. She is using selective attention to only focus on her book, but maybe she's actually listening to a conversation from the gazebo behind there. Selective attention, you can kind of redirect that. A specific example of this is called the cocktail party phenomenon. Cocktail party phenomenon is the idea that you can filter out a pretty wide range of other stimuli just so you could focus on one conversation. The way somebody could at a party or maybe in the cafeteria, that there's a lot of conversations going on and you can tune out the one at your table to kind of hear the conversation that's going on at the next table. That's a specific type of selective attention. Our last thing here is sensory adaptation, that when you're exposed to a stimuli for a long time, you don't notice it. Our brain actually does a better job picking up on changes in stimuli than constant stimuli. So we adapt to things over time. So for example, wearing a Band-Aid, you forget you're wearing it. Jewelry, your glasses, your wallet in your pocket if you're a guy, or getting into a cold swimming pool. You get used to that. So sensory adaptation happens unconsciously. Now, the pool example, I feel like if it's a really cold pool, you're going to notice that, and it's not necessarily unconscious, but a lot of times it's unconscious. Habituation is what it's called when we are consciously trying to block something out. So, for example, maybe we're in our classroom and there's a loud noise outside, and there are construction workers there and they're making noise, or they're cutting the grass, or the band is practicing outside. But when we decide, okay, I need to not listen to that and I'm going to listen to Ms. Thomas talk during class, then that would be habituation, because you are consciously trying to block that out and focus on something else.